This actually is a pretty picture of a comet. And comets, we're going to see, actually, the only one they get close to the sun do they fizz like this, right? So what we've kind of been talking about asteroids and comets all along, but what they have in common is they're leftovers from the formation of our solar system. Okay. So starting with asteroids. Most asteroids are found in the asteroid belt, of course, between Mars and Jupiter. So asteroids tend to have this kind of weird shape, kind of like the video said. Most of them are not rounded. Only gravity can kind of round them, and only if they have a certain amount of mass can they be kind of smoothed over. Most of them look like potatoes like that. So like I said, most asteroids are in a space after the last terrestrial planet before the first Jovian planet, so between Mars and Jupiter. And actually, the reason they didn't form, it's thought that Jupiter actually plays a role in making it so that another planet didn't form there, the gravity of Jupiter. Let's see, what else? I was going to take you right quick to Dawn. Actually, Dawn is a NASA spacecraft that actually, it first visited Vesta and then is actually now orbiting Ceres. Ceres, C-E-R-E-S, actually may ring a bell. Ceres actually there is the largest belt asteroid, and it's actually another dwarf planet. So, let's see if the internet's working. Actually, no, I don't think it's. All right. So, moving on, actually there are different types of asteroids. Most asteroids are located in the asteroid belt. You want to know where the other ones are. Okay, the other ones, actually, this is a term on your unit exam, Trojan asteroids. Trojan asteroids are associated with more than just Jupiter, but the planet Jupiter actually has a series of asteroids escorting it in front of its orbit and behind its orbit. They are what we call stable Lagrange points. Okay, kind of work with me here. Either work with me or, I don't know. So actually Earth has some Trojan asteroids too. But most notably, Jupiter has the coolest Trojan asteroids. There are asteroids that we worry about crossing Earth's path, and those are generally called Apollo asteroids. This one right down here is actually kind of showing you what I said a minute ago. The asteroid belt, the region between Mars and Jupiter that has the kind of crumblies that actually would not add up to be a whole planet, but the gravitational influence of Mars actually makes it so it didn't kind of, what we say, coalesce into its own little planet. All right. Actually, and I don't think that the video did any, it almost kind of continued this myth of if you're in the asteroid belt, you'd actually have to be dodging asteroids. They're actually quite far apart from each other. All right. Meteors, and meteorites. And as they are on the slide, they actually are in the order that they occur. And I think the video did a pretty good job. Meteoroids are kind of like asteroids. Can you see the O-I-D-S in meteoroids? So meteoroids actually just a smaller version of an asteroid. So it is a space rock. A meteor actually is that flash of light that you see as something, a space rock, is falling through the Earth's atmosphere. Okay, so meteors don't last very long. So a meteorite is actually what these kids are touching. So on the video, you saw that meteorite hit that car. I thought that was pretty darn cool. You know that was worth a piece of cash. Okay. Oh, the skies are all orange out there now. So meteorites can actually be worth a lot of money. I thought the video did a good job in giving actually you kind of an image of a guy holding these space rocks, these meteorites that made it through Earth's atmosphere. Did you catch the part in the video that said how much matter the Earth picks up every day just because of stuff falling through the Earth's atmosphere? It's amazing. Most meteorites are micrometeorites, and actually there's a whole way to go out there and find those. Sometimes students will bring me a rock and they're like, hey, is this a meteorite? I'm like, I don't know, let's send it to Iowa City and find out. So those are asteroids. Comets are similar, they just have an icy component to them. Okay, they were formed actually on the cool side of the frost line. Okay, and it's thought though, I say they formed on the cool side of the frost line, but this video actually said that they're thinking that sometimes the comets look like they've been processed so that actually are closer to the sun than you think. So this seems like something we've talked about. There are actually two locations for comets, two main locations for comets. I like what the video said because the video was like, well, how do we get a comet coming close to the sun? And actually it mentioned like Neptune kind of giving a gravitational tug to, I thought that was pretty cool. So we have the Kuiper Belt, which actually lies in the plane of the ecliptic, and then we have the Oort cloud, which is a spherical region. Most comets are minding their own business out there, and they never flare up, and they don't make that tail, that sort of thing. And if I go too fast, let me know, but it looks like we're doing okay. Okay, so comets only flare up if they get close enough to the sun. And so, like I said, why do they ever change their trajectory from the Kuiper Belt or the Oort cloud to become, close enough to the sun to flare up? Again, it's the kind of a push. I've also heard it could be a push from a star, from a nearby star. I don't know. So you're kind of seeing some comets in action right there. Okay. They call it sun grazing, actually, as the comet. See, figure the comets, everything in the Oort cloud is gravitationally held to our solar system. So basically, they just get a nudge, and that means that they come into near the sun, and then they go back out. And instead of being kind of an ellipse, it's something like what they call a hyperbola or a parabola. Okay, so basically, it goes really fast when it's near the sun, near perihelion, and then it's slower out here. And these can take thousands of years to kind of return once they have a new trajectory. They can go around the sun about 100 times before they all kind of basically fizzle out. Comets, as you may know, NASA has caught comets running into the sun, like kamikaze comets. So, poor things. And this website up here, let's see if this will work. Nope. This website up here, heavens-above.com, I think I've shown it to you before, but in light of this topic, I might have mentioned that there's a comet this fall going to be in naked eye visible, but the one I think I was thinking of is only in more like the southern hemisphere. So, well, that's not going to work. Let's go on the next slide. Wasn't meant to be. Okay.
So it's not called Halley's Comet then, is it?
What's not called Halley's Comet?
They pronounce it differently, like in the movie.
I don't know. Could go either way. There's a lot of things they pronounce. Like, did you hear that two different people, the Kuiper Belt and the Kuiper Belt? I'm like, whatever, I think that they get less hung up on it as maybe some other people. So, I don't know. Halley's. This actually is Comet Lovejoy, and these are taken through my telescope last fall. So, comets, this looks like all coma. You don't really see much tail. And I kind of tracked Comet Lovejoy. I got some pictures throughout its time. It's not, you can't see it now, but I can't see much of a tail there. Oh my gosh, now what's it doing? Oh, goodness. There you are. Silly. All right. So the anatomy of a comet kind of looks like this, where this figure does a good job. They have the nucleus, and I like what this figure did because this little thing right here, that's the nucleus. So that's like a nucleus in an atom. It's the center of the comet. You can kind of see the fizz. It looks like an Alka-Seltzer tablet, right? Then actually we have around the nucleus is the coma. So on the Comet Lovejoy and my pics, actually the green thing was all just coma, no tail. That's kind of common. There are actually two types of tails that are associated with comets. There is the plasma tail and the dust tail. The plasma tail goes directly away from the sun, as kind of indicated here. So if this is the sun, okay, this is the plasma tail. That's kind of how that works. And the reason for it is one of the things we said, and we're going to see this with all stars, is the sun is blowing solar wind. So basically it's a positive pressure that blows that plasma tail. So with regard to the direction of the tail, it gets kind of funky sometimes. Over here you see, I like this figure too, you see that's actually the comet before it begins to fizz because it's not close enough to the sun. Okay. Here it's starting to kind of get a coma. And then here when it gets close enough to the sun, it actually starts to get a tail. But you see where the tail actually is always directed away from the sun. So here it's directed away from the sun, the plasma tail anyway. All right. So let's see if this will go. This was a busy summer for people, amateur astronomers or people who are just watching what NASA does. Because this summer, I already talked about the whole New Horizons, who visited Pluto, okay, this summer. This summer also, earlier this summer, the spacecraft Rosetta actually chased a comet, okay? And Rosetta has inserted itself in orbit around the comet as the comet's moving away from the sun, I think away from the sun, not towards the sun. And actually, not only that, but Rosetta had like this little spacecraft that it sent onto the comet. And so, this isn't going to work either. But notice this was not a NASA gig. This was a European Space Agency gig, Rosetta. So, well. Oh, it did go out. I know, that's why it does that. Okay. So all it does what you want it to do, or what you ask it to do. Come back. All right. Well, that's not good. Okay. Here it is. So I'm still not taking a lot of your time, but I wanted to show you just a few things. Rosetta. All right. So, yeah, ESA stands for European Space Agency. And so these were actually, many of these, that close-up picture, for instance, was taken by the lander thing. So I just think that is so cool. And can you imagine them holding their breath? And let's see. Seems like that's a little video. Maybe not. Maybe that's all it's going to do. But that is so cool. Oh yeah, there's a little video. Okay. So this actually, this isn't it, it's the next one, but here's a close-up of a comet doing its thing, fizzing, okay? This was mentioned in the video we saw. Remember where basically another spacecraft orbited a comet and basically sent down an impact thingy, okay? And this is actually showing the impact. It created a crater on this comet, Comet Tempel 1. So kind of from left to right you see the still images. Because one of the things, actually, the video talked about that NASA has been tasked to do is to find those near-Earth objects, NEOs, and then the other thing is to have a plan how to make it so they don't impact the Earth. And so you can imagine, it said you can either break it up or you can try to deflect it. This actually kind of showed that it's harder to break up than you might think. Just made a crater. All right, so meteor showers, actually I'm trying to keep track of our meteor showers. But whenever somebody says there's a meteor shower in progress, basically what's happening is that the Earth is running through debris that was left by a comet, usually a comet. Remember, as a comet gets too close to the sun, it begins to fizz, and kind of in the path where it is, it leaves some of its guts, okay? And so as the Earth passes through that comet guts, basically it's creating a situation where the Earth is running into a lot of stuff, and those stuffs create streaks in our sky that we call meteors. Remember, meteor is kind of the streak that the thing makes as it falls through the Earth's atmosphere. Okay. So I like this picture, like the top there, it kind of reminds me of, when you're driving in snow, what it feels like. That's not a very good effect. Okay, but it's similar to the Earth kind of driving through comet debris, and then some of that debris falling through the Earth's atmosphere and creating a meteor shower. So yeah, right here, you mentioned Halley's Comet. Actually, the Orionids was created by Halley's Comet, and it peaks about October 22nd. So we have something peaking November 3rd, November 17th. The big ones, though, are actually the Geminids, okay, is a really big one. And another big one, as I think when we started out the semester, I mentioned, is the Perseids. Those are really big. So you figure the Earth actually, when the Earth passes through the comet debris, that's when you get a meteor shower. And that happens kind of like clockwork every time of certain times of the year. That's why we have meteor showers at certain times of the year. Okay. All right. And the name of the meteor shower is the constellation that it seems to come from. So the Orionids come from Orion, the Perseids come from Perseus, the Geminids come from Gemini. All right. So it seems like we've seen this a few times, but how about one more time? Hopefully you'll be able to explain why Pluto was demoted. It was demoted basically because they finally defined a planet, what a planet is, and the criteria it didn't meet. And actually my mom was watching like a NOVA show recently, and she called me up. She's like, I know why Pluto's not a planet anymore. I'm like, yes. And she explained it to me just like this. Okay, so this did not clear its orbit of debris. So the problem is basically if you look at Pluto's orbit, there's basically other it's Kuiper Belt stuff. There's other Kuiper Belt stuff out there in Pluto's orbit, okay? Because my mom was like, so if they didn't reassign it as something other than a planet, we would have had like 1 million planets. I'm like, you're right, okay? And that's exactly right. So the thing that demoted Pluto was, remember we saw actually this video last week, the discovery of a potential planet Eris and its moon Dysnomia. Okay, so but these are actually Eris and Pluto and Charon, Pluto and Ceres, there it is. These are actually all known as dwarf planets. So that's cool. All right, so actually, the video did a good job of talking about this incident. Remember when they talked about a really powerful comet flying through, not our atmosphere, but flying through Jupiter's atmosphere. And it made those cool little plumes. That's all this is talking about. So it's pretty exciting. Then we've talked in the previous chapter how Earth has basically resurfaced itself, got different ways of doing that. And actually I'm not going to take you to it, but if you would Google Manson meteorite impact, that's actually Manson, Iowa. So there actually is a meteor impact site here in Iowa. So then there's always the famous why the dinosaurs died. And I think the video did a good job talking about that. So I'm not going to talk much more about that. I'm not sure the video, I hope it did. It talked about this picture right here actually is trying to emphasize that As you excavate rocks, actually, you know that basically, if they're sedimentary rocks, basically they leave a layer of stuff, and then on top of that is a new layer of stuff, and on top of that is a new layer of stuff. So as you go down in rock, you're actually going back in time. So actually there's a layer of rock that coincides with the demise of the dinosaurs, and that layer of rock also has a fair amount of the element iridium. And iridium is unique to asteroids, comets, space rocks. Okay, the element iridium you're not just going to find in a layer like that. So how did the dinosaurs die? And I think they probably talked about this too. Basically, it stirred up dust, it blocked the sunlight, caused plants to die, and then the herbivores died, and then, of course, then people who are animals that eat the herbivores also died. So will the Earth be struck again by a major impact? Probably. Okay. Actually, it wasn't in time for the video, but this actually was back in
2013.
Yeah, thank you, 2013, right after Valentine's Day. So over in Soviet Union, basically they had an asteroid fly by. And in Soviet Union, apparently everybody has dash cams on their car.
Literally everyone.
Apparently.
That's insane.
Our daughter wants one of those, so I don't know if she's going to get one or not. But it will happen. And I could take you out to NASA NEO program, but you can Google it if you want to. Basically, it would show you that NASA, like I said, like the video said, has been tasked with tracking. NEO stands for Near Earth Objects. Near Earth Objects. And there's actually been private organizations trying to raise funds and look at this issue because they want their grandchildren not to worry about they're going to like all die. So I don't know. All right, so the last slide-ish. So this actually was also addressed kind of earlier in the video about the role that the gas giants played actually to help kind of gobble up and kind of deflect otherwise harmful asteroids and comets coming in to hit Earth. We're just so lucky. All right. So let's go ahead and take a look at Chapter 10 real quick. This is my first semester to include Chapter 10, but I think I like it. Chapter 10 is, like I said, very brief, and it looks at planets orbiting other stars. After your test next week, we're going to take it looking at actually our sun and then looking at stars in general. So it's kind of nice. We're finally getting away from planets. Yay! Okay, but before we get away from planets, let's look at planets that orbit other stars. There we go. All right, so one of the things right off the bat is we talked actually of the different types of astronomy. We're all about visual astronomy, you know, but remember there are some other important types of astronomy, including infrared, looking at images in infrared. Now, infrared actually is looking for thermal signatures. Okay. Now, usually we cannot see planets directly. Okay. This is a very rare example of actually seeing the thermal signature of planets directly. Instead, we see planets indirectly. And there are two ways we can see planets indirectly. All right. So by far the most obvious way is indirect detection. So the term extrasolar planet just means a planet that's orbiting a star other than the sun. Okay, and actually though, we should apply what we know about the formation of our solar system using the nebular theory, kind of apply that to other stars, other planets being formed around other stars. Seems reasonable. Okay, as of 1992, that year, they didn't know that there were actually about 70% of the stars have a planet, at least one planet orbiting about them. Okay, so since then they've actually found at least, or nearly it says, 2,000 planets orbiting other stars with an assortment of characteristics. We're going to see that some planets are easier to find than other planets. But what makes it challenging, like this last thing says, what makes it challenging to see those planets is how small they are, okay, and how close they are to the host star and the blinding light from the host star.
So basically, you want something that's big and far away from the host star.
Yeah, big and
Like
far away from
Jupiter.
the host star. Yeah. The problem, though, is if it's too big, and this is actually my slides, if it's too big, or if it's too far away, it takes so long to orbit that these techniques, you can't see it indirectly. So, I don't know. It's tough. So the two types of indirect detection, this one has to do with gravity. Actually, the sun and Jupiter actually do this sort of dance, okay? It's kind of shown down below there. Basically, there's a wiggle because a planet is so big, okay? There's a gravitational tug from the large planet, and it makes the star move a little bit. And so those two figures kind of show that. So there's two ways to see that movement. One way, astrometric, that's just a big, terrible, scary word. Astrometric, okay, all it means is basically you are actually, you are looking against the background stars. That's all it means. It means you literally can see it move against the background stars. That's what astrometric means. The other type of movement we've talked about actually is a shift, a Doppler shift. You get a blue shift if it's moving towards you. You get a red shift if it's moving away. And that's actually being shown right here. So there's the two ways of seeing the wobble. The other indirect method actually is what's called a transit or eclipsing method. And so in that one shown here, basically, and it only works in a certain sort of what we call line of sight. So this figure right here is trying to show you that only if kind of like the plane of the ecliptic, whatever, is like in your line of sight and you see the planet move in front of the star and behind the star, is this going to work? So what you do is you shine a light meter, and actually these two kind of insets are showing you the light meter. Basically, the light goes down as the planet moves either in front of or behind the star. Oh, God. I think I just go outside and talk. So, things that we can actually measure about a planet. I'm so confused. Things that we can actually measure about a planet. I'm trying to figure a way to do this, keep my sanity. Because measure about a planet, like indirectly. So all of these are things that we can measure. You know, we can measure how long it takes to go around the star. That's, of course, the period. How close it is to the star. Again, about its orbit, how eccentric its orbit is. These are actually probably more things we care about. What's the mass of the planet? Okay. What is the size, the radius of the planet? What's its overall density? If we know its density, we have a sense of what it's made of. And what's its atmosphere like? That is so cool. Can you imagine indirectly what's its atmosphere made of? This is actually looking at a particular star, Kepler 11. The reason it's called Kepler is because actually there was a spacecraft, and I think it's out of commission now, but we're still looking at its data. that spacecraft orbiting the Earth, all it did was basically to study stars and to look for, I think it was this transit method, to look for planets orbiting other stars. So it can be done, it has been done, it is being done. So when we look at our solar planets versus those planets that orbit other stars, what do we see? Well, we're a little bit limited to the planets that we're seeing. Like I said, we're kind of seeing the close-in planets, and like Kate said, we're seeing the large planets. Okay, we're kind of missing the small ones. So we generally see them that there's some kind of head scratchers out there. They tend to be kind of the gaseous planets instead of the terrestrial planets. But if you're like me, every once in a while you'll hear in the news that, NASA found an Earth-like planet orbiting a star in the Goldilocks zone. Have you ever heard that term? Basically, it's where water can exist as a liquid. Okay. So this is the last slide, and I don't have a whole lot to add to this. Each one of these dots represents a planet that they found and kind of the general characteristics. Okay? All right.
Question.
Yes,
So what we just did, was that chapter 10?
that was chapter 10.
No.
6 slides. And I have the review thing to go ahead and give you.